All right, hello. Before we start, can you do me a favor and sign in? Okay, and then one thing which is not ideal, I made the 18 handout based on the book and also like my dumb idea of the schedule, because I assumed this week would be all 18 and then next week would be 19, but he's kind of like mushing it together. So I need to make a 19 handout and I'll probably send that to you like on Wednesday or something. And then we'll skip some of the 18 handout because I put some stuff on there that's useless for this class. Then we'll just start 19. I don't know, I'll figure it out. But most of it's okay, so we'll just use it. Okay, anyways, let's just start. So keto and enol forms are what, and how do you go in between them? In enantiomers? Tautomers, yes. They're tautomers, and then how do you go in between the tautomers? That's the name of one of them. But how do you go from keto to enolate? Yes, and a base, yeah, is going to do the proton transfer. So you go in between tautomers by transferring a proton. And that can be acid or base catalyzed. Yeah, it could be both. Okay, so now we have this enol. And I'm asking, is it a valid resonance form of acetone? And acetone looks like this. Yeah, so the proton moves, which means it's a tautomer, and proton transfer is not resonance. That's like its own thing. So tautomerization is not the same thing as resonance. That's important. Okay, and then just as a reminder, this form on the right of acetone is the keto form, and then the one on the left is the enol. It's like super simple because this is obviously a ketone. And then with the enol, you have like your alkene, so the ene, and then your alcohol up top, so the all. Okay, so out of these 4 keto things, which one would exist most in the enol form? Yes, because yeah, it would have the most stable carb anion. We're not really looking much at the carb anion specifically. It's more like the overall structure of this entire thing. So the last molecule drawn out as an enol, remember it's proton transfer, so we just take one proton from here and then turn it into an alkene. So when we actually do turn one of the ketones into an enol, it turns into this like 6-membered ring. The 6-membered rings are very stable in general because the bond angles are nice and happy. In this form, you don't get that like 6-membered cyclic structure. So it's not as stable as this enol form. And then what actually like completes the hexagon is this hydrogen in the middle. So when you do transfer that proton from the CH2 up to the oxygen, this hydrogen can now be shared between the 2 oxygens. So that lets it be a ring. In all of the other examples, you don't get this kind of structure with like the shared H bonding. So they're not going to be nearly as stable. It's possible in this one, like maybe this ketone would rotate up and then you get something cyclic, but I think there would be too many members in the ring for it to be favorable. So the rest are just keto mostly, and then like very minor enol. Okay, and now the mechanism for proton transfer is pretty simple. You can do it with acid or base, but I think it's more common to see it done in base. So I'm gonna do that. Let's say you have NaOH and H2O. So first you identify the alpha protons. So on this acetone, you have these alpha protons on the side. This is what we're gonna be concerned with during the reaction. So you can go on either side, it's the same thing. But all you do, you take your base and then you abstract an alpha proton, and then the bond breaks and then creates a alkene on between the alpha carbon and the carbonyl carbon. And then the pi bond goes up to the oxygen. So it's just a basic elimination reaction. So once you've deprotonated it, you technically have a lone pair on the alpha carbon because the electrons from the hydrogen carbon bond broke and now they're just stuck on the carbon. So in this like transition or intermediate, it's called the enolate. So whenever you're going from keto to enol, you have your enolate intermediate, which is the ion. So in the enolate, you can go between the 2 forms by just moving the lone pair. You can go from this lone pair up to this carbon, up to the oxygen, and then get this form of the enolate. And then to go back from that form, you just move these electrons down and then those electrons back onto the carbon. But if you want to protonate it and get like a full enol, you just take your conjugate acid, so like in this case just water, and then you attack it with the alkoxide ion, and then you get your protonated enol form. So another thing to note, the enolate and enol forms are both achiral. Because it's all sp2, there's no wedged or dash. Okay, so those being achiral allows for something called racemization. So when you're, how do you pronounce this? When you're trying to make a racemic mixture of a ketone, you have to look for 2 things. So first, you have to have 1 alpha hydrogen And then you also have to have a chiral center. So this over here is a chiral center because it's attached to 4 different groups, and it does have an alpha hydrogen on it. On this side, you don't have any alpha hydrogens, so you can't really racemize on that side. Okay, so the point is, if you have on one side of the carbonyl, like if one of the alpha carbons is a chiral center and has 1, you can go in with your acid and base, do your elimination, and get the enolate. So in this case, it's acid-catalyzed. So you just protonate, this, then it has a charge, and then the proton transfer happens by whatever, the conjugate base. So now you got your enolate, which is, remember, achiral. Oh, wait. So the original keto was chiral, and we just turned it into the achiral enolate. Remember, the keto and enol forms are at equilibrium. So you can imagine, like, when they equilibrate back and forth, the chirality is also going to change. So let's say we go in with water now and give the alpha proton back. We're just going to stick a proton back on the alpha carbon. This proton can be added from the front or back. So it can be added back either wedged or dashed. So that changes the chirality of that chiral center. So we can get one version where the methyl is dashed like it was originally, and then we can also get the other version where the methyl is wedged and the hydrogen is dashed. And then you're going to have 50-50 because obviously there's no preference for which direction the hydrogen gets added back on. So you end up with your racemic mixture of products. So remember, if you have a keto that has the chiral center, 1 alpha hydrogen, and you put it in an acidic or basic solution, it's going to go through racemization. It's always 50-50 racemic mixture. Okay, so for this next ketone, we see that there's only one side that has an alpha hydrogen on it. And it's also a chiral center. This carbon is attached to 4 different groups, so it's also going to go through racemization. In this case, it's base catalyzed. We don't really care about the mechanism. All we know is that keto in basic conditions goes to enolate. So the enolate is going to look like this because all you have to do, get rid of alpha hydrogen and then like kick up this bond. So you know the oxygen becomes negatively charged and you get an alkene over here. So I'm just going to do that. So now when I go back to add the alpha hydrogen, it's the same thing's going to happen. You're going to get a racemic mixture of products. So the important thing to note here is that you have deuterium. So you will have to, like, instead of leaving it as like an invisible hydrogen, you're going to have to label it as like a D. So when the enolate goes back and attacks, we get two products again. The deuterium can attach from either the front or back. In this case, it came from the back because it's dashed. Then you can also make it wedged. Doesn't matter, just a racemic mixture of both chiralities. Okay. So halogenation, if you're given a ketone and these reagents, like X2 over some kind of base, what do you think happens to the ketone? And alcohol and bromine? Yeah. Yeah, so it forms an enolate, and then with an enolate, you know that the alpha carbon has a negative charge. So with that negative charge, it just goes and attacks a bromine. So basically what's happening, you have your alpha hydrogens, you're just substituting an alpha hydrogen for a halogen. So the mechanism for this, first you have your base, which takes the alpha hydrogen, forms the enolate. So you have this. Then the enolate is reactive and the bromine, one of them is electrophilic. So the enol just goes up and attacks one of them. So then the final product, it's what I said, you just get rid of one hydrogen, add one bromine to replace it. And depending on how much of the halogen you have in solution, you can do it multiple times. But this is just a general mechanism for all halogenation. I'm not sure. I think you probably get a mixture because I don't think OH minus has a preference for like hindrance. Is it add another line or it's just at the end? Yeah, it's like this is the alpha carbon, then new bond between that and bromine. Okay, so here's the thing. The two bromines, like you need the two bromines together to make it electrophilic. So bromine is like negatively charged, it's nucleophilic. So if you have like the conjugate base, like this Br minus, it's not going to go back in and attack this Br minus because there's nothing to attack. It's nucleophilic. So you do need excess Br2. That's instead of excess Br2. Yeah, probably. If you have enough equivalents, you could probably halogenate both sides. Yeah. Okay, so that brings us into the HVZ reaction, which is basically just halogenating carboxylic acids. So this is the thing you showed you in lecture with the protecting group and then the Br2. So the first step of this is to like protect the reactive alcohol of the carboxylic acid. So remember what reagents we could use to do that. Yeah, SOC would work if you're chlorinating it. What's the bromine equivalent of Sockle?
Oh,
And then you can also use like PCl whatever and PBr. Any halogen protectant group. All that does, just turn the OH into whatever halogen you have in the protecting group. So yeah, now we have our enol intermediate. Which is just the acyl halide. This acyl halide does switch between keto and enol. So the alpha carbon does have a negative charge on it, which makes it reactive. Okay, so now that we have that, we can give the molecule like a halogen, Cl2, Br2, I2, whatever, and then some kind of catalyst. And then all that does is that it attacks the new halogen, but not from the like alcohol side, it attacks from the alpha carbon side now, because we have the enol. So from the enol form, we're giving it Br2, so it's gonna attack one of the bromines, and you just get a halogenated alpha carbon. And then the very last step, you can leave it like this as just like a dibromo something. But if you give it water, you're going to turn this portion back into a carboxylic acid. So this bromine would just stay, but this way you just revert back to a carboxylic acid. So if you do this to completion with water, the only transformation that happened was just halogenating this alpha carbon. Good question. I had the same one, but I just accepted it. So yeah. I would assume it would do an SN2 on the bromine, but it doesn't. Cool. So the other halogenation we're concerned with is the halo form reaction. So with the halo form, you're basically just taking a ketone, giving it a bunch of halogens and a bunch of base, and your final products are a carboxylate ion, or if you protonate it, a carboxylic acid, and then something called a halo form. So yeah, when you see a ketone and then these reagents, like 3 equivalents of a halogen, 3 equivalents of a base, or just halogen and base in excess, you can just basically assume you're making a haloform. So what happens in this, the abridged version, you have your 3 alpha hydrogens again. So in this reaction, the excess bromine just keeps replacing alpha hydrogens until you get like a ridiculous amount of halogens on 1 carbon. So from the mechanism that I showed you before, it just halogenates. So you get something like this. And then now the important bit is that you get 1 more equivalent of base come in and attack the carbonyl, because at this point the carbonyl is very, very electrophilic. This like tri-bromo thing is super electronegative, and it's taking a lot of electron density away from the carbonyl. So now what we do, we go in with some extra OH minus, attack the carbonyl, and then this carbon with 3 bromines is so stable as a leaving group, it just pops off. So your final products, like I said, are your carboxylate from where the OH minus attacked, and then your halo form, which looks like this. I don't know why, but like when I was taking the class, I always assumed this thing was called the halo form, because that sounds so much cooler than like the CHBr3 being the halo form. But this is what it is. That, I mean, you could probably go in with an acid and protonate it, but yeah, I don't really know what the point of this is. It's just like something you can do. But yeah, let's just move on. So when you're making your enolate, you are not always going to have acetone, so you're not always going to have a symmetric ketone to deal with. If you want a regioselective product, like if you want the ene part, the alkene, to be on one side versus another, you're going to have to change the base you use to like deprotonate. So, well, first, on this molecule, there's 2 alpha carbons, right? And then 2 alpha hydrogens. There's 2 options for the enolate you could form. So which one would be the kinetic one, do you think? The left or right alpha carbon? The right? It would be the right. So if you go in on the right side to form an enolate, it would be the kinetic one. Oh, that's a horrible color. And then if you were to go and abstract a hydrogen from this side, you would get the thermodynamic one. So now, how do you tell the difference between these two? Like, what makes it kinetic versus thermo? The number of, yeah, what about the number of hydrogens? Yeah, so if a carbon has more hydrogens, it's less sterically hindered. So it's a lot easier to abstract the hydrogens. So on this CH2, it is a lot more hydrogens than like this, which is just 2 methyl groups. So it's a lot easier for a base to come in on this side and abstract from here. So for the kinetic enolate, the side with less steric hindrance, that's the one you're gonna put the alkene on. Yeah, I guess a good indicator of steric hindrance would be the number of hydrogens. So more hydrogens, it's easier for the base. The kinetic enolate is not really formed at equilibrium. For the thermodynamic, it's allowed to like equilibrate between forms, and then you kind of end up with like the more stable alkene. But the explanation doesn't really matter. Just know it's not at equilibrium. And then if you want to get the kinetic enolate as your major product, you want to use something bulky and hindered. So that's going to be something like LDA or LIHMDS. They're like very big, very hindered. I think they look like big crabs. And I'm just like, okay, it's like a big crab can't really go in and take a proton that easily. So to prefer the kinetic enolate, you're going to use bulky base, and then an aprotic solvent like DMSO or THF. So on our left side, to go between the ketone and the kinetic enolate, I would use LDA over THF. Okay, and then for the thermodynamic enolate, you have to look at the alkene stability. So this alkene is tetra-substituted as opposed to this one, which is tri-substituted. So tetra is more stable. So for the thermodynamic enolate, you look for the more stable alkene. And it's also going to be the major enolate at equilibrium under thermodynamic control. The equilibrium thing is really not important, but occasionally there are some like word questions, word problems that are like, I don't know, under what conditions would the thermodynamic enolate be preferred? And then to get the thermodynamic as the major product, you want to use like a hydroxide ion as your base, like a hydroxide or alkoxide. So like ethoxide or hydroxide. And then you're going to use like the conjugate acid as the protic solvent. So the reagents I pick to go from this ketone to its thermodynamic enolate, I would just use like ethoxide over ethanol. All right. Yeah. Okay, so might as well just move on. So we saw halogenation through an enolate intermediate. We can also do alkylation. It's literally the exact same idea. So given a ketone, a base, and then an alkyl halide, what do you think is going to happen? Mm-hmm. Yeah. And then what does it do? Yeah. So once you have your enolate is nucleophilic at the alpha carbon. So we can just take the alpha carbon and attack the electrophilic alkyl halide. And then she's right, LDA is a bulky base. So we're gonna form the kinetic enolate. So this side is less hindered. So most of the enolate is going to be this form with the alkene on the less hindered side. So now that you got your enolate, give it an electrophile and it'll attack. So here we have an alkyl halide. We just take attack from the alpha carbon because it has that lone pair on it. And does an SN2 reaction with the alkyl halide. So just goes in from the back, and now you have a new carbon-carbon bond. So this was an ethyl iodide. And the main idea here is that you're replacing an alpha hydrogen with like this alkyl portion. So this is an ethyl iodide. So we're getting rid of one alpha hydrogen and putting an ethyl where it was, just substituting it. So your final product, you get this. On this side? Yeah. Because LDA deprotonated on this side because, yeah, prefers it. Okay. He went over alkylation in class, right? Did he go over like alkylating twice? Okay, great. If you alkylate twice, it's like a little bit of a different story, but if we're not concerned with that, that's great. Okay, anyways, it's the exact same story with the esters. So where do you think the LDA is going to deprotonate? The left side? There is no alpha carbon on the left side. Oh, like you mean here? Yeah. It's not going to be acidic enough because on this one you have the resonance, there's nothing here. Yeah, so it has to attack the right side because that's the only alpha hydrogens on this molecule that are acidic. So LDA has no choice. It goes in, takes this, forms your enol. Enol and alkyl halide, what happens again? Yeah, you just attack and attach the alkyl portion of the alkyl halide. So in this case, we have a methyl iodide. So we send in the enol to attack the methyl, get rid of the iodine, and then you just have now a methylated ester. Yeah, nothing really happens on the oxygen side. It's just no, it's just kind of inert. Okay, so alkylation is pretty straightforward. Deprotonate, alkyl halide, attach the alkyl part. But there are some limitations. Because it's in a solution with a strong base, you can get like elimination product as your major product if you're not careful with which alkyl halide you use. So the only things you're like allowed to use for alkylations like this at the alpha carbon are primary alkyls, primary benzylic alkyls, and then primary allylic alkyl halides. So yeah, those are the only alkyl halides you're really allowed to do to alkylate the alpha carbon. The rest are just going to be silly and eliminate themselves. Yeah, it wouldn't happen. Yeah. Okay, so now this is the part, I don't think he did this in class, and I don't think he's like very concerned with like specifically like acetoacetic esters or whatever, but it's the same idea as the rest of the chapter, so we might as well just do it. Acetoacetic ester? Really?
He just didn't show us like 3 years old, like that.
Okay, I don't, okay, I must have been really, no, but he was showing you like different condensations and stuff. I don't, is that the same thing? Yeah, this is like different.
Yeah.
Okay, whatever. So with these kinds of things, you're basically, you have this CH2 in the middle. It's very acidic, so we can deprotonate it and add stuff to it really easily. So we're basically just trying to alkylate this position and then cut off one side of the ester. So in the first step, you're given ethoxide over ethanol and an alkyl halide. So what do you think happens when it reacts with this ester? You form the enol. And then what does the enol do? It attacks the ethoxide? Not yet. What attaches? This thing? Yes. So once you have your deprotonated enol, you just go into the alkyl halide and then attack. Then you get an alkylated ester enol thing. Well, there's no choice for kinetic or thermal. Maybe like if he gave you something like this and then LDA, you would probably deprotonate here. But in those cases, he also like adds stuff to this carbon, so it's less confusing. So it would be pretty obvious that you'd have to take from this side because there's stuff on here. More substituted where? It's not because it's more substituted. You take from there because it's more acidic, because it's in between the two carbonyls. So it's easier to deprotonate from here because it's better resonance stabilized. from here, there's less steric hindrance, but you only get resonance with one carbonyl, which sucks. So after that step, you just attach whatever your alkyl was. So in this case, it's a propyl group. So you just attach a propyl to, what do you call it, the alpha carbon. And then you're giving it sodium hydroxide over H3O plus. So what do you think this does to our little molecule? It does. So it's going to just hydrolyze the ester into a carboxylic acid. And then in the last step, the point of the last step is to just decarboxylate. So you could decarboxylate with just heat, or you could go in with your lithium hydroxide and DMSO. And that decarboxylates, so it just cuts off the carboxylic acid. So the point of this reaction was to take like your kind of beta dicarbonyl thing, protonate the carbon in between them, and then cut off like one of the ester portions. So you're just alkylating and like getting a substituted ketone. So you want to go from your like acetoacetic ester into your substituted methyl ketone. So since this gets cut off, you're left with this to work with, and then you're adding whatever to one of those carbons. It does not matter. But straightened out, it looks like this. Yeah. Okay, it's 150, so that's all. I will make another handout for chapter 19 and send it via email. And then we'll probably do that on like Friday. And that'll be all like the condensations and stuff he did today.